I don't know how to fix it. So the equation switched to the other side of the graph
Oh,
when I was downloading it. And I think somehow we didn't change it back over. And I don't know what to do. Would you like me to print it off?
if in doubt, or make a, just write a note somewhere that I'll see it, just explain. This equation shows up over here, but it really goes with
Okay.
something
Yes,
like
sir.
that.
Okay.
Yeah. The bizarre things I've seen is I've saved a document as a PDF. And so then I look at it, it looks just like I expected to. I post it, somebody uploads it, and suddenly a picture has gone to normal size or has slipped around, or
Yes, sir.
I don't understand why it does that.
Yeah.
Anyway, stretch your legs. Don't smoke them if you got them, but if you need a water or something. So let's talk a little bit about, this is from the lab due on Thursday. And sort of filling out that last table. Table 4. There it is, it's the last one. So this would be somewhat similar to, the numbers are not accurate, I just made them up on the spot, but would be similar to trial 5. I have the weight of the meter stick, I have the weight of the 200 gram mass, I have 4 scale 1 measurement and 4 scale 2 measurement. And what I ask you to do in the next to last table is to put down the forces. So 4 scale 1 was 4 newtons. 4 scale 2, 3 newtons. They're both up, and I said make up positive. Weight of the meter stick, or I worded it more awkwardly, but because it is down, it's -1, and from the 200 gram mass, it's down, so -2. So those are the forces those are the known forces. If I add them up, I should not get 0. Now, the total force should be 0, it's in equilibrium, but if I'm adding up only some of the forces, it shouldn't add up to 0. And if I add these up, I end up with 4. So this is my sum of the known forces. But I know if I add up everything, I should get 0. So only thing I'm missing is that unknown. So if I added up all the forces, it would be 4 plus 3 minus 1 minus 2 minus question mark is equal to 0. Well, I know that this adds up to 4. Actually, let me change that, plus the question mark, since we're not going to assume a direction. What does the question mark need to be in order for my total to be 0?
-4.
Yeah, so 4 plus -4 is 0, so the force due to gravity from the unknown is -4 newtons. That is the first column of that last table. So that is the force. The negative sign is indicating direction downwards, which is what I would expect. The next column deals with the magnitude. Now the magnitude doesn't care about direction, so since that minus sign is a directional thing, what is the magnitude of this force?
1.
Yeah, so the magnitude, so the second column, I'll have 4 newtons. Now that force should be the weight of the object. I know that the weight of an object is equal to mass times acceleration due to gravity. I know the weight, it should be 4 newtons that I found experimentally, and that's equal to the mass times the acceleration due to gravity. Now, connecting it to the master set 2, this value varies depending upon where you are. In that lab, 9.798 meters per second squared. Now, how do I know that? Well, there's a generic formula, but if you look out about here, you got Silas Creek Parkway, and it's Miller Street, I think, is the one right on the corner. Is that Miller? It's either Miller or Ebert, whichever one it is. The next one, if you come this way, there's gonna be a road that tees into Silas Creek. There's a median there, and then you got Forsyth Tag. In that median, they actually did gravimetric studies to figure out what is the acceleration due to gravity there. There are not many places that have the actual study done that close to the campus. That's where that comes from. Now, at this point, they've actually, and I checked a couple other sources, and it all still came out to be about the same thing. At this point, they've mapped close to the entire world. All right. On the moon, it's 1.625 meters per second squared. How do I know that? Because I went on to Google and I typed in G moon, and it gave it to me. All right, so to find mass, well, the math problem is 4 is equal to m times 9.798. That's the math problem. How do I isolate m? So if I divide by 9.798, I will get the mass, which will be somewhere a little bit more than 0.4. If someone actually be kind enough to. And by the way, on a test, if you need a calculator, we have spare calculators that we can lay down during classes. 0.408. What would the units be?
G?
Not G.
Kilograms.
There we go. K. Kilogram. Now, unit-wise, I have newtons here, and I divide by meters per second squared. So I have a newton over a meter per second squared, which naturally, of course, is a kilogram. Actually, the reason why it is because a newton is a derived unit. I think I mentioned that before, and a newton by definition is a kilogram meter per second squared. So if I divide by meters per second squared, I want kilograms. So 0.408 kilograms. So that is the next to last column. Now the last column is percent error. Now it's going to be a repeat of some of the stuff that I said to people individually, but percent error assumes that there is a mistake, which means that there is assumed to be a correct value. The correct value is what you measure directly when using triple beam balance. It would be on that lab, if you turn the page over, it's that number in the space that you wrote down at the bottom. So it varied depending upon what you use for your mystery object. So let's say that from direct measurement, just putting it on the triple beam balance, I found the mass to be 0.350 kilograms. 3501. Let's just all right. Excuse me. Now to find the percent error, I first need to figure out how far am I off of the correct value. So I just find the difference. So 0.408 minus 0.30501. I think I said it wrong, but it's written right. 7 carry the 1, 9, 7. All right, so I'm off by 0.0579 kilograms. Is that significant? Well, we need to compare it to something else. Because I could be off by that much, and if I'm measuring the distance from here to the moon, yeah, if that's in meters, that's not particularly significant. If I'm measuring the mass of an atom and I get that in kilograms, that's way off. So I need to compare it to something. Well, since there is a correct answer or assumed correct answer, I compare it to that. So I take that difference, 0.0579, and I divide by the correct answer. That's going to give me some fraction. And someone would be kind enough to actually tell me what that is.
165, 4.
Yeah,
1564.
no, you're right, 165, sorry.
65.
I'll just tell you the
All right. Now that is the decimal form. I want to get into percent form because I'm asking for percent error. So I multiply by 100. That moves the decimal point over 2 spaces. So my percent error is 16.5%. For whatever reason, other than the usual childhood scars, I think everywhere on that in the tables, I put the parentheses in units. But for here, I don't have anything in parentheses. In which case, you either need to put the percent symbol in parentheses, so you don't have to write it down, or you put the percent symbol after the number. Most people put the percent number after the number, but some people just individually just don't write it. Yes?
So where did you get that .3501 from?
I just made it up. I said, let's just assume that was the correct answer. That
Oh.
you measured that on, you took your mystery object, put it on the beam balance, and got it.
So the unknown?
So for yours, it's that number right there, yes. Questions about this part of the lab?
Can you explain the percent error one more time?
All right, so whenever you're trying to figure out how far off you are, you need to give some sort of perspective. For example, if we were trying to guess each other's age, and I'm 59 and you said 61. I'm trying to guess your age. I don't know how old you are. I'm just going to make up a number. Let's assume that you're 20 and I say you're 18. So we're both off by the same number, 2. But is that a significant, is 2 years, how, does that really mean that we're just equally far off? Well, 2 years at your age and 2 years at my age, those are very different impacts. Me at 61 and me at 59, probably not a whole lot of difference. A person at 20 and a person at 18, there is a lot more difference there. Or take it one step further, a person at 1 and a person at 3, huge significant difference there. So when you find the difference between things, we need to give some perspective. And so we give the perspective by comparing it to what the right answer is. So in this case over here, or let's just take, let's say 59 is the right answer, and 61 is the experimental answer. Well, the difference is 2. And then to give some sort of sense of, is that a good answer or not? Well, you divide by the correct answer. And then put it in percent form. By multiplying by 100.
Okay.
Is that sufficient or?
Yeah. Yeah.
Not really wanting to confuse matters at the moment, but we will run into a slightly different thing, which is called percent difference. That will show up, and we'll worry about that when we get there. Ms. Sasson does one pop quiz, and that quiz is knowing the difference between percent error and percent difference. I don't, but I am tempted, so. I won't subject you to it, I'll give you the answer. Other questions about this stuff that I covered? All right. Other questions from that lab? Questions from Master Set 2? Did it?
Did I hit the button?
it's flashing, good.
For the first one, flip your axis.
Seems like there were some
with
questions
the X
from
on top.
Master Set too, that
Put the Y
I guess
on
people
top,
had
and that's
epiphany
what,
and-
that messes up the
everything's
numbers,
good. Oh,
the way
yes.
we're measuring,
I'm
so.
just really confused on 11.
Which one's 11?
I weigh
Yeah,
a
so
book
put
on
the
Earth
X
and
on
get a
top
weight of
and put the
21
Y on the bottom.
newtons.
All right, so let's talk about mass and weight.
How we should have to say. Put the X on top.
Now, most of the people in 110 have a lot of biology experience, and my understanding is that mass and weight are used interchangeably in biology. I haven't had biology since the late 70s. I don't know. I've suppressed those memories. In physics, we cannot use mass and weight interchangeably because we deal on a different scale. We deal with global scale, and also weight is a force, mass is an indication of how much inertia an object has. So they perform different functions in physics. Probably a decent enough definition of mass is how much stuff something is made of. So I have more mass than probably everyone in here because I have more stuff in me. And the older I get, the more that stuff is called fat, but I was working on dad bod over the summer, and I got closer to it.
I think I weigh more than you, I just carry it differently.
Maybe
You said you're how much?
200, 220.
I think I weigh a little bit more,
Okay.
just being honest.
Okay. People who don't carry it as well. All right, so no matter where I am, if I could somehow teleport to the moon, my mass would still be the same. Mass is not dependent upon where I am, because it's, again, how much stuff I have here. And so if I go someplace else, I still got the same amount of stuff. Weight, on the other hand, weight depends upon the acceleration due to gravity. How much is the Earth or the planet or the moon or whatever actually pulling down on you? So on Earth, if I take my mass, it's about 100 kilograms, times 9.798 meters per second squared, I would have a weight of 979.8 newtons. If I went to the moon, again, my mass doesn't change. So that is W is equal to mg. Still using the same formula, W equals mg. My mass is 100 kilograms, but the acceleration due to gravity is less. If I stood on a scale and was in equilibrium, what the dial would show would be different, because the acceleration due to gravity on the moon is 1.625 meters per second squared. And if I multiplied that out, I would have a weight of 162.5 newtons. So I can lose almost all my weight without losing any mass at all. I could also lose weight on Earth by just going up to farther away from the Earth. So if I went to the top of Mount Everest, brought a scale with me, because what else would a physicist do on Mount Everest? I can show that my weight is different up there than it would be down at sea level. Matter of fact, your weight's gonna be a little bit more at the poles than it is at the equator, because the Earth bulges out at the equator. So, in the problem on the master set where you're talking about, I have an object that weighs 21 newtons on Earth and 21 newtons on the moon, that right there is setting up for finding the mass. Because I give you the weight on Earth, G, or 9.8 is fine. This is the lab number, 9.8 is fine. I think somebody did 9.81, sure. 9.805 if you want to go slightly more precise there. And so you find mass doing this technique. On the moon, you're doing the same technique, the only difference is that number is 1.6 or 1.625 or somewhere in that range. But the fact that things weigh less on the moon, even though it's the same mass, things weigh less on the moon is one of the reasons why the moon does not have an atmosphere, is that it couldn't hold on to the air. Which is one of the reasons why terraforming Mars would be very difficult. Because I think its acceleration to gravity on Mars is 3 point something meters per second squared. Right. Did that help? Okay. Did you have a follow-up question? Okay. Other questions on master set 2? Okay. Chapter 3. For those keeping track of that. We've already touched on some of it, but let's actually give some additional context for our meeting. As mentioned before, there are certain words that automatically mean we're dealing with a vector and direction matters. And there are certain words that when we hear, we should automatically think, oh, scalar, I don't care about the direction. Set up our list here, vector. A vector quantity, position. Now, the symbol that I use for position, there are several of them. I tend to use X a whole lot, just because. Again, childhood scars. X, Y, Z, R, S. Those are the most common letters used when trying to figure out position. And then part of and they've got the arrow on top to indicate we are dealing with a vector.